Hi everybody, welcome back. Now, if you remember in our last video, we talked about finding out the critical points that existed on our Quartic function. What we discovered through our quick little analysis was that the advanced function part of it was that x-intercepts occurred at 0, and that in fact turned out to be our only x-intercept, and that our y-intercept was also at 0. Then what we did next was we took the derivative and we used the derivative to figure out points where the slope apparently was 0. And the points where the slope was 0 turned out to be at 0 and at x equals 3. Okay, and that's what you're seeing on the left side of your chart here, the portions of the derivative that made up the derivative function and then the derivative itself. So just to make sure you're aware, the chart that I've drawn on the screen that you see here is the chart that incorporates the calculus information that we will be using. When I took the second derivative, I found something interesting. I found out that in factored form, the second derivative came out to be x minus 3 and x minus 1. And when you set those equal to 0, what you get is 1 and 3 again. So we had this really interesting property that a critical value of the second derivative also matched up with a critical value of the first derivative. And what we'll do is we'll run the numbers through the chart and see what we come up with so that we can then try to come up with a full analysis. So just a reminder, in case you didn't remember, the purpose of the question was to fully graph the function y equals x to the power of 4 minus 8x cubed plus 18x squared. Okay, and what we're going to use is a calculus interval chart to take us through that process now. So let's go ahead and start out. If you see along the top of the chart, I have made the intervals of the function based upon the critical values that I discovered by setting the first and second derivatives equal to 0. And then I've simply made the intervals according to from negative infinity to positive infinity. Okay. So the first interval we'll examine is this interval here, the one on the left-hand side, and we'll pick a test point. Okay, test point we will pick has to be between 0 and negative infinity. Why don't we just pick -1, and we'll plug -1 into each of these component parts. Okay, so -1 plugged into 4x produces a negative result. -1 plugged into x minus 3 squared produces a positive result. And remember that x minus 3 squared times 4x will be a positive times a negative, because these two components made up the factored form of our derivative, and they would be multiplied together. Okay, the factored form of our derivative was 4x bracket x minus 3 squared bracket. Okay, so a positive and a negative is a negative, so our derivative is going to produce a negative slope for our function along the interval of negative infinity to 0. Second derivative, we plug in -1 right here, and what do we get? Well, we get a negative result, and we plug in -1 to x minus 1, and we get a negative result. And negative times a negative produces a positive. So that tells us that the function has a negative slope and is concave up along the interval from negative infinity to what? To 0, right? Negative infinity 0. So our function would therefore have this kind of shape along that interval. Okay, now let's go up to the critical value itself, 0. At 0, if you plug it in, this is 0. If you plug in here, this is a negative result. But 0 times anything produces 0. So the derivative is 0 at x equals 0. Once here, we're going to have a negative result. Here, we're going to have a negative result, and a negative times a negative is a positive. Okay, so before we define this feature, let's just hold off for a second. Let's go on to the next section. Let's pick a value now between 0 and 1, which is our next interval right here. Okay, so let's pick 0.5. 0.5 times 4 is positive. 0.5 minus 3 squared will be a positive. A positive times a positive will produce a positive, so the slope will be positive. And for second derivative, 0.5 minus 3 is negative. 0.5 minus 1 is negative. So we have a negative times a negative, which is a positive. All right. And now this is really important because now what we see is the following. We see in the previous interval where x was 0, or the previous point where x was 0, we had a 0 slope and a positive second derivative, so indicating concave up. And also really important, the function changed from being, negative to positive, which would indicate a minimum as well. So the combination of a 0 slope with a concave up second derivative suggests to us that at x equals 0, we have a minimum. Okay, now let's go to x equals 1. At x equals 1, what do we find? Well, we get this result here is positive. We get this result here is positive. We get a first derivative that's positive. We end up with a negative here. 1 minus 3 is negative. We end up with 0 here. So the second derivative is going to be 0, which means no concavity. Okay. Before we do that, let's just make sure that we don't forget that the function in this region appeared like this, that arrow that you see there, because we had positive slope with positive concavity. Okay, so we got an interesting situation at x equals 1 because the second derivative is 0. So now let's figure out what it is. So now we'll go to our next interval, which is from 1 to 3. We'll plug in 2. So this will be positive. This will be positive because you're going to be squaring. The result is the first derivative will be positive. This right here will be negative. This right here will be positive. A positive times a negative is a negative. Okay, so now look what's happened. We have a function that has changed concavity. So here, the function didn't have any concavity happening because it had in this line here where 1 was occurring, right? We had 0 concavity, and here the function suddenly now in the interval from 1 to 3, when I say here, I mean from 1 to 3, we have a positive slope with negative second derivative. So the function now is doing this. The function has changed concavity from positive to negative. So guess what? We must have a point of inflection, I should say. A point of inflection where x is equal to 1. Point of inflection. Okay, point of inflection. All right, interesting. Now let's go to 3. At 3, we have positive. We have 3 minus 3, which is 0, right? 3 minus 3, which is 0. So the first derivative will be 0. 3 minus 3 again is 0. 3 minus 1 is positive. A positive times 0 is 0. Okay, so let's now, before we figure out what's going on here, let's just hold off judgment for a second. Okay, so now let's take our final interval, 3 to infinity. Let's pick 4. 4 times 4, positive. 4 minus 3, okay, squared, that's a positive result. Interesting. The first derivative is positive. What we have here is we have 4 minus 3, positive. We have 4 minus 1, which is positive. And a positive times a positive is a positive. Oh, wow. So this is really interesting. The function is concave up positive. And take a look at a very vital fact. The second derivative changes sign over that critical value, but the first derivative doesn't change sign. In order for it to be a maximum or a minimum, the derivative must change sign. If the second derivative changes sign, then we got a point of inflection. So we have a really interesting case here where we have another point of inflection, another POI, okay? Even though it's a zero slope, the thing is that the function doesn't change signs, which means, when I say that, I mean the derivative doesn't change signs. So that means that it can't be a turning point. Okay, in the next video, we'll take all this information that we've gained from the chart and we'll put it into a graph.